All right, so let's get going. So program for today is a simplicial model for the loop space. Okay, so we were talking about loops yesterday, so let's talk more about loops. Before I have I'll go back to loops in a second, right? Actually, no, not in a second, in like late in the lecture, because in the end, I'm aiming at giving you a simplicial model of the loop space, but I say what simplicial things are, and then give you some examples that will help you understand this model, because if you don't have examples, it'll be, yeah, I can claim what it is, but I don't know. I'll try to convince you it works. So I start with simplicial sets. Okay, definition. A simplicial set x, y dot is a collection of sets y k, should we call k greater or equal to 0. So for every natural number I want a set with together with maps. Maps, and there are two types of maps. There are the so-called face maps. Faces the I from yk to yk minus 1. There's one for every I between 0 and k. And there are the so-called degeneracies, which are called Si from yk to yk plus 1, so it goes up. 0 I k, like the other ones, okay? K plus 1 of each for every k. And they satisfy such that star. That. Okay? So I wrote it up ahead of time. The simplicial identities, they're called, okay? Why not? What's the idea? Why? What's the idea? What should you have in mind? Yk is like the set of, it is also called the set of all so-called k simplices. Okay? K simplices, we have talked about simplices. You should think the k dimensional, so think copies of the k dimensional simplex, delta k. Okay? This is my set of copies of delta k. This is my yk. Example, yk is going to be, for example, our singular set sync k of x. Now x is a space. This is all the maps from delta k into x. So this is a very big set, this one, but this is a fine set if I want. It's a lot of k simplices in a space. It's all the possible k simplices in a space, in this sense. Okay? I could have taken all the injective maps also if I wanted, or something else. No, I could not, but so far, yes. But it wouldn't have worked. We'll see why. So let's take all maps. So yk is this, and then what about these di's and these sj's? Di, this tells us who are the k plus 1 faces of any sigma in yk inside as objects of yk minus 1, okay? K plus 1. So remember the k simplex, it has k plus 1 faces. This is a 3 simplex. So they are of dimension k minus 1, but there are k plus 1 of them, okay? So if I think of my yk as a set of things like this, then it should have k+1 faces that are objects in the previous guy, because these are lower dimensional, okay? Yes?
Should DI tell us which one is the I of those?
Yes, yes. So DI is a map from yk to yk minus 1, okay? So I know exactly which one is which, okay? I have k+1 such maps. Example is, of course, in our singular set, we have seen these DIs. These are the DIs, right? Think K, have we seen them? Maybe, sort of. Right? I've said these were there. DI, think K minus 1, X. Maybe I want to say them, well, it's given by, so DI of a simplex sigma, which is a map from delta K to X, is the simplex. So DI sigma goes from, not very nice notation, dk minus 1. I include as the i's face, the map I call DI, delta K, and then I do sigma. Okay, so I restrict my map. I have a map from delta K into X, and I can restrict to the i's face. Right. Okay. So this is what you should have in mind for the faces. What about the degeneracies? The SIs, yeah, they're a bit strange, but they are to make many constructions work. When you first see simplicial sets, you say, why do we have to carry around these bloody SIs? Actually, there are things. I have now started to work in some contexts. It's good to work with what is now called semi-simplicial set, which was the old name for some simplicial sets. But nowadays, semi-simplicial sets mean you don't have the SIs, and you pretend you don't need them. And in some situations, this is good and this is better because it's a much smaller thing. But in practice, there are many constructions where you need the SIs. Okay, but these. Yes. Yes.
Are semi-simplicial sets usually simplicial sets? Are there?
Can you add? Yeah, you
sets?
can always add all the. There are. Yeah, you can add all the possible degeneracies, right? You can do that, but this is. But this, then you create something huge, right? Yes.
I see. So you can have.
Yeah, you can go. Yeah, but these, so there. I had a master student work, who in the fall, who wrote a master thesis about, the difference between going simplicial, semi-simplicial, and things. And by the end of his master thesis, I understood why. I think he too. We understood why simplicial sets, degeneracies were necessary. Once you start doing homotopy theory, and then you can say, okay, but I just go back and forth with some fun things. But as soon as you start doing this, you will blow up your simplicial. These constructions, the degeneracies will show up. If you try to not have them, they will come back. So that's what it is. Anyway, so they are here. Why are they called degeneracies? Because they are degenerate types of things. What do they do? In the example, you should think of these as the degenerate. So the images are images of are the so-called degenerate simplices. And why are they degenerate simplices? Example in, if I go think k x to si to think k plus 1, what is it? Of x, it's going to be, again, a precomposition. So I have a map sigma from delta k to x. And I'm going to create a map from a bigger delta k, so si sigma of sigma. This is a map from delta k plus 1. And what do? I crush delta k plus 1 to delta k. I lose the dimension. This is, I'll give you the map. And then I do sigma, right, to x. So I crush it, and what do I do? Well, this is the map that takes, elements here were 0, t, 1, t, k plus 1, 1, okay? These were the elements in delta k plus 1, a sequence of, and I just forget, Si forgets Ti. Okay, so I collapse the simplex. I have k plus 1 different ways of collapsing the k plus 1 simplex into a k simplex. These are, crushing maps, so they are degenerate in the sense that they will create simplices that forget a lot of stuff. Good. So that was simplicial sets. Oh, I thought I would also. So I've given you. This is the maps. Si. What have I? Maybe I should write these. Where do I write? I write here. So delta k was this set of the subset of Rk, T1, Tk, in Rk, such that 0, T1, Tk, 1. And I've been using Si. I'll try, but I fail sometimes to write an upper I when I do this map. There's a map Si from delta k plus 1 to delta k for every I between 0 and k plus 1. That takes T1, Tk plus 1 to T1, the I hat. I forget the i's coordinate. That's the one I just described. And then there are maps di, which are the ones I used here. This. When I pre-composed here, there are maps di from, which are the face inclusions, delta k minus 1 to delta k. Again, 0 I k. And these depend a little bit on I. If you have done the exercises yesterday, you will sort of already know what they are. D0 of T1 Tk minus 1 is 0, T1 Tk minus 1. So I add 0 in front. The I in the middle is Tk minus 1. I just repeat Ti, T1 Ti, Tk minus 1. And then dk, the last one, so this is 0 I k minus, up to k minus 1. And then dk, tk minus 1, at the 1 at the end. And you can see that these are the boundaries of the simplex, because the simplex, what are the boundaries? It's exactly when one of these is an equality. And we have this is exactly what we've done. Okay? So these are the faces, the k plus 1, the k plus 1 of them. These are the k plus 1 faces of the simplex. Good. Simplex. Yes. Of course, what I've been saying, this is a little bit also why, we're going to play with the simplex in many ways. Yesterday, we talked about the singular chain complex. So in the exercises today, I guess. Yes, exercises today. So exercise. C star x. It's z of this. Z. It's like, if you do z coefficients, think star x. Okay, we were talking formal sums of these maps, so they have something to do. And the differential is the sum minus 1 to the I of the di's, differential in here. The simplicial exercise, the simplicial identities there for the di's imply that d square is equal to 0. So simplicial identities star over there imply d square is equal to 0. And so once, yeah, this is how these things fit together. Okay, so the singular complex is an example of a simplicial set which we've seen. There are many more examples. One way to get examples is to take categories. Example, if C is a category, there is a category. You can construct a simplicial set out of it. There's a simplicial set. The nerve, it's called the nerve of C. I'll write it NC for nerve, is the simplicial set with, so how do we define it? And the 0 simplices, I have to tell you what each set of simplices is. The 0 simplices is the objects. Okay. The 1 simplices is the morphisms of C. So I make a 1 simplex for every morphism. And more generally, NK C is the set of composable morphisms. So I have A0, F1, A1, F2, A2, brr, FK, AK. So this is like the composable morphisms. In the category. Okay? So I've told you what the simplices are. I have to tell you what the DIs are and the SIs. DI of I have to do them one at a time. The DI is D0 of something like this. A0, F1, brr, FK, AK. It's I just forget the first one. So it's A1, F2, F2, FK, AK. Okay, so if I had only one morphism, if I had just one guy, then I forget it and I'm left with an object, A1. Okay, so that would also work here. The I of something like this is composed at the i's position. A1, da, da, da. I get to AI minus 1, and then I do up to AI plus 1. I forget AI. So I go Fi plus 1, Fi. Compose with Fi, and then I keep going. AK, Fk. Okay, I can do this for every I between not 0 and not k, but otherwise this makes sense. You can forget AI, that's what we do. And then the k, you can guess, is just a drop the last, right? So A1 up to AK minus 1, and I forget. Thanks, 0. I dropped the last, not the first. Oh, thanks. Yeah, it's because I was copying. Shouldn't copy the previous line. Anyway, I had to copy here and I didn't do it, therefore I did it here. Okay, thanks. Yes, so di I compose here in the middle when I is not 0, not k, and otherwise I drop the first or I drop the last. Okay? It's easy to remember. And I'm just lacking the SIs, so I write them there. SI, that's easier. It introduces an identity. So it goes A0, and then somewhere I arrive at AI plus 1 to be precise, and then I do identity to AI plus 1. So I repeat AI plus 1, and then AK. Okay, and this makes sense for every I between 0 and k plus 0 and k n. It works. What?
You do it at I, not at I plus 1, because as 0, you do it at A0, right?
I do it at I, because I want to do it at A0 also. All right. Not here an I plus 1. Somewhere else there's an I plus 1. Okay, if I missed an I plus 1 somewhere, this one maybe. Ah, this is the one. Here. Right? Because I needed the 0th one here. Okay, somewhere there are I plus 1s, not here. Some people are upset. Okay, I think that's correct. Ooh. Yes. Yes, I need this to make sense between 0 and k. 0 and k. There you go. This was also wrong. 0 and k. 0 and k. Yes, I think that's now correct. Okay, yes?
For DI or above, I can't read and don't remember what the math in the middle first we started with D1. A composition of
D1 you would compose the first two maps. This one you're asking?
yeah, just what does it say about the error?
It's Fi plus 1 circle Fi.
Yes, you compose the two maps. Yeah. Yeah? Yes, all right. I think they're correct now. Okay, so claim they satisfy these identities is not very difficult to check. If you have never seen this, it's a fun exercise. You'll see why there are these shifts and things. And if you think of forgetting the AI or adding an identity at AI, you will see, you increase, you decrease, you do it at different places. It's not too difficult. Okay, I'll let this as an exercise. We have to go back to our circle at some point. No.
Can we see C star X as the error of some category?
Yeah, let's try. Okay. The objects would have to be C0. Let's think star, right? The simplicial set, right? This one, right? So let's do simplicial sets. Otherwise, we have to do simplicial abelian group or something. Okay? Let's do simplicial set. The objects would have to be the maps from a point into X, so the points of X. And then the morphisms would have to be the intervals, right? And we would have to, so you have to think of, what's the boundary. The boundary map is, you would have to think of an interval as going from, as a morphism from its value at 0 to its value at 1. And then you have to ask, maybe, then I have, I can compose. No. The answer is no, because, then I would say, okay, these are my morphisms are the intervals, and then I can compose, of course, when they join, and then I would have a 2 simplex for every of these guys, right? But these would be intervals. But now in that thing, I have many more things. I have all sorts of maps that don't care about the intervals. So I think no. Yeah. Okay, so when you think simplicial sets, we should also think about spaces. It's all about spaces, so leave this one for a bit. So to a simplicial set, we associate always a space. And when we think, I said think of yk as a set of k simplices. Now we'll make yk a set of k simplices in a geometric sense. So not this one. Yeah. So definition. So the realization of a simplicial set. Simplicial set y dot is the space. So it's a topological space, which we usually write like this. And what do? We take, for every k, we take yk, which is our set of k simplices, and we put a k simplex for every k simplex geometrically. Right? So we cross with delta k. Okay? For every k simplex, I put a k simplex. But now I remember how my simplices are attached together according to my face maps and degeneracies. So I mod out by an equivalence relation, which says if I take a y, if I take the the boundary di of a little y, point t in the simplex is equivalent to, let me write it and then talk about it, y di t, where y is in yk, say, and t is in delta k minus 1. So for all such, we glue them and we do the same with the degeneracies. Si y t is equivalent to y si t for all y, say in yk, and t in delta k plus 1 then. So what are we saying? We're saying if I have my y, my y is a k simplex. Okay, I attach in my realization, I attach an actual k simplex corresponding to y, but y had a face. Here there's a guy which was called, there was a guy called diy in yk minus 1. In yk minus 1, it is attached to a k minus 1 simplex, and I'm saying these should be glued together. So the face is the face. That's all this is saying. It's a bit maybe difficult to see the first time you see this, but this is exactly what it is saying. The face in yk minus 1 of this, whenever it is, any point of the k minus 1 simplex, is attached to y on the boundary of its k simplex. And same with the degenerate guys. If I take a degeneracies of y, you remember that was like you should think crush the simplex. This is saying, well, if this guy is a degeneracies of y, its coordinate t should be crushed and attached to the guy for y. Okay, so the degenerate simplices will not show up in some sense in the realization. They are identified with things that are non-degenerate. Yes?
On the left, the spaces are right, but for I guess for the D1, but on the right, y is in yk, and D upper I, okay, cool.
Yeah, it goes up, yeah. Yeah, this is sort of, so there are a bunch of exercises for the exercise session. If you haven't played with simplicial sets, there's a simplicial and there's a co-simplicial going on. There are the DIs going down and there are the DIs going up, and we are going to play a lot with up and down and up and down. So I try to write up, indices up when they go the other way. So that's the trick, but I sometimes fail, of course. Okay, so, but that's, you can always make a realization. So, an example, if we were in the nerve of a category, in the nerve of C, if I take the realization, then whenever I have a 2 simplex, for example, A0, F1, A2, F2, A1, A2, F2, like this. This is a 2 simplex, okay? This was an element in the nerve 2 of C. Then this should give me a 2 simplex in the nerve, which is a triangle like this. This is the triangle called F1, F2. And what are these things saying? It's saying, well, D0 of this thing should be attached to its D0. So let's not worry about where D0 exactly is, but I told you over there, we could write coordinates. We could do this precisely. D0 is I forget the zeros guy. I forget the beginning. So I have F2. I want to put it here if I'm allowed. So I'm going to glue F2 here. And when I do D1, I should compose these two guys. Okay, so somewhere I should compose, and we want to put them here, F2 of F1. And D2, I should forget the last guy, and so I have F1. So somewhere, so the three boundaries, somewhere they go around the simplex in this way. There's F1, F2, and F1 of F2 of F1. And what are the boundaries of these boundaries? F1, its boundary is, well, D0 is A1. I don't have anything here, I just have A1. And D1 is A0. So this is something, and I feel like putting A0 here and A1 here, and this is the correct placement if I write my coordinates right. F2 will have boundary A1 and A2. And this is A1 and this is A2. And this composition will have boundary A0 and A2. This is how they fit together. Okay? So every time you have a composition of arrows in your category, you have if I have k arrows, there will be a k simplex that goes F1, F2, F3, and then I can do more, so F1, F2, F3. And then everywhere else it will be compositions, partial compositions of your arrows, and the vertices simplex will be these k plus 1 elements, A0 up to AK. Okay? And wherever on an edge you know what composition to write. It's the composition that goes from the AI to the AJ. Okay? So that's what it looks like for a category. Okay, so the reason I wanted to do this construction for the category is because we're going to go back to the loop space, right? And the loop space has something to do with the suckle. And so I want to give you a simplicial model of the suckle. And it won't be a category, but it will be morally a category. And this is the only way I can think of it. And so therefore, this is how I'll present it. Example. So we want a simplicial model of S1. And I'm not going to say this is the simplicial model of S1. There are tons of simplicial models of S1. This is the simplicial model of S1 that will fit what we want to do tomorrow. Okay, so which is why I put it. So what's the idea? Is we're going to pretend we have a category. What does S1 look like? Well, S1 it looks like this, right? I have my. If I had to give you a cell decomposition of S1, that's what I would do. I would take 1 point and one-dimensional cell. So we'll try to do this as a simplicial set. And I'm going to think of this as a category. Let's call it E for the edge. Think a category with one object, this guy, and one morphism, E, but, well, one non-identity, thank you, non-identity morphism. This point will have an identity, otherwise I don't have degeneracies. So I want an identity. That reminds me of something. But one non-identity morphism, but E not composable with itself. So it's not a category because I'm not allowed to compose E. But otherwise, I will build the simplicial set exactly as I build the nerf. Just I'm not allowed to put 2 copies of E. So we'll, yeah, okay. Yeah, that we.
Or can we just say E squared is somehow equal to identity? Like define that relation?
E square equals the identity.
Like E composed with E is equal to identity.
E,
Say that it is
no, because then you would have to write E composed with E in your simplicial set, right? There will be a 2 simplex that says E is the identity, and I do not want that simplex. Okay, so let's just write out what it is, right? So so now what is let's call it S dot. I'm going to write it like this. So what is S0? Okay, I'm doing I'm thinking category, so how many objects? One object. So S0 is that object. That's it. I have 1, 0 simplex. Yeah, so far so good. S1, how many morphisms do I have? So S1 was the morphisms. 1, no? 2. What is the other one? The identity, okay? So there's the morphism we all, because I drew it, which is E, but there's also the identity. Should I call it one? Identity. Let me write identity. Okay? I can also put the identity. And then, what is S2? Let's try S2. How many morphisms in S2? Oh, how many? So now we have to write sequence of composable morphisms, but I only want to write equals. So we have identity. This is a happy simplex. Then we have, I could do E once first, E and then identity. And then I could do identity and then E. Okay. So you get the picture. Yes?
Please tell me, an example that is not satisfy the definition of simplicity.
That does not satisfy the definition. Well, so for example, so let me then use that to say a remark that I wanted to make anyway. So let's do a non-example. So let's say I was being more innocent and I tried to do so mark y dot y0 is equal to just a point, y1 is equal to E is, a semi-simplicial set, but not simplicial set, but not the simplicial set. I can define D1 is equal to D0 from Y1 to Y0 to be, it's a set with one point only, so there's only one map, so I make them equal. This is like the zeroth boundary of my E is equal to this. This looks like a circle, it's a good start, but what about my SIs, right? But S1, what is, I need an S1 from, I could do S1 from Y0 to Y1, this is fine. That's a unique map, no problem. But what about S0 and S1 from Y1 to Y2, which is empty? Okay, no map to the empty set. So simplicial sets are so that if one guy is non-empty, everybody has to be non-empty because I have maps in all directions. Okay, so either it's the empty simplicial set or it's infinite, it's non-empty in every single dimension. Yeah?
But is it enough to just think about the non-degenerate simplices then? Just to say that we have these non-degenerate simplices and then everything else that you need to be in your set, make it degenerate and just put a name on it.
Yeah, this is what I was trying to say. It's not as, this is what one wishes. And in many ways, yes, I guess. Yeah, maybe.
So
In some situations. But we will,
for example, this crazy simplicial, not crazy, nice simplicial set that we had, its geometric realization is a circle.
It's a
It has
circle.
only two non-degenerate sets.
Yes, you will see what will happen with all these degenerate things. They will be there. They will keep, even if we didn't have them, what I will do would not work. We will need them and they will play their role. So, there are some situations where, yes, you can just think about the non-degenerate. For example, if you think of the realization, but when you start doing things, you will need the degenerate. Oh, depending on what you do, right? Yeah?
So when you allow E to compose with itself.
No. So we need to write.
But you still get something homophily equivalent to S1, right?
Yeah, homeomorphic actually. Yeah. SK. So let me just write the general guy. SK is, well, we have the trivial, I write them small, identity. And then we can do E, identity. This is the general guy, right? And then I can do identity, and then I do E, identity. And I go up to, I do identity, and I put E at the last position. Okay, so that's my general guy. And we can think of them as, this is 0, this is 1, this is 2, up to K, right? So in the exercises I tried, and now we know, and so there are K plus 1, so SK has cardinality. Cardinality of SK is K plus 1. And we know what the boundary maps are, because they're the same as in the categories, right? D0 is I drop the first DI in the middle, I compose somewhere. I know how to compose identity and E, that's all I have. And DK, I drop the last guy. So this is a well-defined thing. And SIs, I include identities. That's also no problem. Okay, so it's a well-defined simplicial set, and it has cardinality K plus 1. You can identify in this way the objects, the K simplices, as being the numbers between 0 and K. In the exercise set, I tried to write these maps in terms of the Ks. I think I got them right, but maybe there's a mistake. I think I got the maps right. But you can write the maps, and it's a completely combinatorial thing, right? It's the numbers between 0 and K plus 1, 0 and K, and their maps. Okay? So you can write them. You can forget about this picture. But I don't know, this is the way to think about it. So claim, and I leave this as an exercise also, is that if you take the realization of SK, of this simplicial thing, it is S1. And, you already sort of know this, because the only non-degenerate simplices are the 0 simplex and E. Everything else is crushed onto it. Everything else is degenerate stuff, right? This is crushed to the base point. It's a big K simplex, it's crushed to the base point. This is crushed to E. This is crushed to E, and so on. Okay, so you sort of know. There's nothing else but the circle. Good. Fine. We have a model of the circle. So we are ready for the loop space. So back to the loop space. There should be a co here, which I didn't say. Simplicial. Of the loop space. So what was our? I need space. Yes.
Do you always think of a simplicial set then as the nerve of some category-like object, or?
No, we just went through an example, right? The singular.
No, so it's
No.
not category.
Oh, does it always work like that?
It doesn't. Not. I mean, okay.
No. Yeah, that's. I mean, I guess you can. It's more than that. It's like, I mean, there are things like, in the nerve, these are particular types of.
Oh, right. There are no two simplices or something.
in the nerve, if I have one simplices that match, if they go, it's 0 boundary to 1 boundary, 1 boundary to 0 boundary to 1 boundary. These are two composable morphisms. I know that there exists a two simplex. So this is what is called, this is a filling condition. So so these are particular types of simplicial spaces. Yeah. More questions? So I'll just say, simple thing is just to say what was LX, right? LX was the maps from S1 into X. We were looking at all the continuous maps from S1 into X. And I've just said S1, I can write it like this, right? So this is the same homeomorphic, because it's a homeomorphic model I claim, maps from this guy into X. Okay, I've done nothing. But what we'll do is try to write out what does this mean. Okay, so what is this? This is, so now in maps from, this was the disjoint union over k greater or equal to 0 of sk cross delta k modulos of relation into X. Okay? Still haven't done anything. I just wrote out the definition. Now I'll do one thing. I'll say, well, this is a little bit annoying. Was a bit complicated. These equivalence relation. Let's forget about them for a minute. Okay? I can forget about them. That means I'm going to look at maps from disjoint union k greater or equal to 0 sk cross delta k x. I say, so these two things are not the same, but there's a map. If I have a map from this thing, it's exactly saying that I have a map from this thing, but they satisfy some relations. Okay? It's not every map here that restricts to a map there, because this has some condition. The map has to be the same on some things that I glued. Okay? So we forget about this. We just say, I can look at what this is to start with. Okay. So we do, what is that? What is that? I have a disjoint union for every k. I have this, right? So for every k, I have to give you a map to X from this thing. Okay, so this is another way to write this, is to say this is equal to the product over k greater or equal to 0 of maps sk cross delta k. That was a k up. It's also a k up into X. So for every guy, I have to give you a map. I used to be afraid of products. You get used to them. Okay, so for every k, I get you a map. And, well, what is this? This is, it's isomorphic to the sets 0 up to k plus 1, k, right? It's k plus 1 elements. Yes, we've just said this. We forget everything about everything. We just remember what it is. It's a set of k plus 1 elements. So what is this? A product of a set of k plus 1 element with delta k. This is k plus 1 copies of delta k. Okay, so this is a disjoint union of k plus 1 copies of delta k. So again, I'm giving you k plus 1 maps from delta k into X. Yeah, same thing. But now I want to write them in a different manner. Another way of saying I can write k plus 1 maps is to say I'm mapping to X to the k plus 1. Okay, so this is equal to product k greater or equal to 0 maps delta k into X to the k plus 1. Okay, so it's just a rewriting of this object. Yes?
So is the reason you didn't allow multiple copies of these so that you would have k plus 1 objects?
So if I had allowed, is it true that, I first would have to think, is it true that the nerve of the category is such that E square is equal to, it's just because to start with, I would have to think, is it even a model of S1? But if it might, you'd think so, right? Because, what? You don't think so?
Figure out that it is not
It is not.
Yeah, because if E squared is
Oh.
0, it's Z.
Exactly. I was just thinking, yeah, a model. I know another model of S1. I know because I know this from all sorts of other stuff that if I take my category to be one object and the integers
Right.
when you compose, you sum when you compose, then I know that this is a model of S1. It's a huge, horrible model, but it's a fact, which I could prove. But this is more complicated. So it's homotopy equivalent. This one is a huge thing.
Yeah, but
Okay.
you have to take all powers of E.
That would be all, but also the negative. Yes.
Explain again with the SK that you get product of the delta.
The last one. This bit. So you're happy with this is k+1 object. So it's a set of k+1 objects cross with this. So it's you can think of it this way, right? I have delta.
Okay.
All right. Yes. Okay. So what have we done? We have written a map, or sort of. I claim there's a map, right? So in here, right? I mean, all the way to the end. So let me say what this map is. Maybe I write it here. Give me one up. So claim the map is going to take gamma from S1 to X. I start with a loop, and I have to give you an element here. What is this? This is a product. So it's for every k, I have to give you an element like this. So it's an F0, F1, F2, to infinity, right? And Fk is an element here, right? It's a map from delta k to x per k plus 1. So for every k, I have to give you. So I have to give you each Fk, and I'm gonna take Fk. It's a map from delta k to x. And what does it do? It takes T1, Tk, which are between 0 and 1. It's just going to, what can I do? There's only one reasonable thing to do, is to evaluate, right? I have, Well, thanks, yes. X to the k plus 1, exactly. We need k plus 1 thing. Okay, what can I do? I have k things here. I can evaluate at T1, I can evaluate at Tk, and so on. I'm missing one. What should I do? Anything reasonable? 0, right? I still have my 0. Why not? Okay, so this is the only reasonable thing I can do is gamma 0, gamma T1. Oh, I don't know. I mean, of course, we could do some function of this, but at least this is, these are the most obvious k plus 1 elements of x that I can attach to this data. Okay? I claim this is the map, and I claim we can see this. Shall we try? So, what is, Fk is the map that is related to this guy, right? When I take Sk. And its value, its i's, in the i's position here, it should be related to the I simplex here, right? It's the copy, it's the map of the copy of delta k that is associated to the corresponding simplex. Yeah? Okay. What does this simplex have to do with S1? The question is how, S1 is here, how was we are in the realization of this simplicial set, how is that k simplex attached to S1 here, right? And how is it attached to S1? Well, it's if k is big, it's a degenerate simplex. We take the big degenerate simplex and we crush it to, well, if E is in there, we crush it to E according to that coordinate, and otherwise we crush it to 0. This one we crush to 0. Hence, when I evaluate, I take gamma 0 for this one. And the other guys, I'm crushing them, and I'm claiming exactly what I'm doing is I'm crushing them to the ice coordinate. This is what's going on. I'll let you think about it, think through it, but it's possible to see. It's correct, it's possible. It's true. I want to say one more thing. Are you allowing me to say one more thing? Yes? Yes.
I think I might have missed something. How are those two equal? So there are 0 to k many copies of this delta k. Now, on the right side, the last equality.
This one?
Yeah.
Yes. I have to give you, it's a map from a disjoint union of copies of delta k into x.
Yes.
This is the same as for each of these delta k, I'll give you a map from.
Okay.
Yes. So the last thing I want to say is I want to say exactly what the loop space is, because I've said there's a map, right, to this thing here. But you can, what did we do? We forgot the simplicial identities, right? So let me just tell you what the simplicial identities do, and as I write them, they'll be so obvious that you will believe it. Okay, so the claim is at X is the set of F0, F1, blah, 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 in this product k greater or equal to 0 of maps from delta k to x to the k plus 1, such that, star, okay, not this one, this is star. And what is this? Well, it's the obvious relations that these maps satisfy, and you will sort of see these simplicial identities show up. What sort of relations do we have? If I take fk of t1, ti, tk minus 1, okay? I have a repeated ti. If I repeat my ti, then I will repeat my map here, right? So this is the I plus 1, I claim, of fk minus 1 of t1, ti, tk minus 1, where this is the I plus first diagonal. I's diagonal, maybe. I's diagonal, I plus first, I's diagonal. Whatever, let's call it the I's diagonal. I'm doubling up a coordinate. In my value in xk plus 1, 2 of the coordinates will be the same. There's an obvious diagonal that does that. If I had a 0, fk of 0, t1, tk minus 1, then this would be the first diagonal, d1 or d0, however you want to call it, fk minus 1, t1, tk. It was the I plus first. You see, I should have looked at my notes. I believed my notes, so this was correct. Okay, let me say why. What is the first value of f is gamma 0, right? It's not the ti's. So if I put a 0, I'm going to double that value, the first one. If I repeat a ti, I'm at position I plus 1 because I moved everything by 1. Okay, that was the I plus 1, it was correct. The I plus 1. Okay, and then, if I repeat the last, T1, if I, not repeat, but I put a 1 at the end, so that's the last boundary map, then this is like a, let me write it D 0k, 1k, something like this, of f k minus 1, T1, there's a minus 1 here, tk minus 1. What does this do? If I put a 1, that means the last value will be evaluation at 1, but evaluation at 1 is evaluation at 0, so it's a diagonal on the 0. I'm putting the zeros guy at the last position. It's a diagonal again. And one more is the SIs. if I forget the I plus first coordinate, according to my notes, f of fk plus 1, that makes sense, t1 tk plus 1, it's equal to fk of t1 ti hat, forget the i's, guy, tk plus 1. Then am I missing one? Anyway, if I forget, if I do fk plus 1 and I forget a coordinate, then that will correspond to not having taken the ti. Okay? So this should look an awful lot like the simplicial things. Identities are just these maps. Okay? The fact that this is a description of Lx is what's going on in that map, not being, we're just describing what it means to satisfy for these maps. Remember, we forgot that they should satisfy these simplicial identities. So it's a rewriting of this thing. Okay. So now I've made this horrible model of the loop space, and tomorrow I'll take this horrible, I'll tell you about Hochschild homology, and I'll show you how this horrible model of the loop space allows you to see the homology of the loop space in an algebraic manner. So it'll be useful, I'll say. Right, enough.